Okay, welcome back everybody to the next session of this webinar. Just to remind you that the meeting is recorded and that you have to pose your question through this button Q&A in your Zoom portal, and they will be taken after the lectures. And we continue with the next presentation from Tilen Potisk from National Institute of Chemistry, and he will update us with the current status of our efforts toward the digital twin of using ultrasound for biomedical applications. So Tilen, please.
Hello everyone. So just let me share my screen. Okay, so what we are developing at the National Institute of Chemistry is a special package in LAMMPS with which one could simulate a lot of interesting multiscale and non-equilibrium phenomena. And what we're focusing specifically is simulating ultrasound via particle-based approach. With that in mind, we have kind of a first step towards a digital twin for ultrasound device. So why ultrasound? So it's being increasingly popular and used in biomedicine, of course, first as an imaging tool, and also as a therapeutic tool. For example, if you have kidney stones, they can use ultrasound to fragment and even guide the kidney stones through fluids. Secondly, it can be used as a diagnostic for various types of cancers. There, they typically use, or at least sense different echo patterns that different tumors produce based on their constituents. It can be used as a thermal coagulation of tissues and so on. And what basically is a propagation of pressure waves through fluids and tissue. You have compressions and rarefactions. But in all of these biomedical applications, you have a certain number of ultrasound parameters such as amplitude, frequency, the actual duration of the ultrasound treatment, the waveforms of the ultrasound packets. And these are all parameters that are typically optimized via trial and error through experiments. And so there is a need for a digital twin. So in a sense, as a code which you could use to optimize these parameters. And we believe that open boundary molecular dynamics is the most promising candidate in this area, and I will explain later why. So this is a general overview of a workflow that you would use to, let's say, use it in a real biomedical application. So in EuroHPC, we have a lot of powerful resources in the form of supercomputers. And through the EESSI environment, you could stream the software that you want. In this case, this would be a LAMMPS code with our OBMD, so this Open Boundary Molecular Dynamics plugin. You could then use that in your own numerical experiments, and ideally, in the end applications, you would use it in a real environment. So to go a little bit on the theory, a lot of systems in nature are open thermodynamic systems. This means that a system does not only exchange energy with the environment, but also mass. So in this sense, particles. And the problem here is that most, if not all, of the MD simulation software packages that exist are dealing with a closed system, meaning a specific or a fixed number of particles with periodic boundary conditions. And so what we're trying to do is just add this part to open up the boundaries and make sure that the system can exchange the particles with the environment. And this is not only with the goal of having this open thermodynamic system, but what it turns out that this framework of OBMD is ideal for imposing non-equilibrium boundary conditions. And so, for example, shear stress, pressure drop during flow, and in this case, pressure oscillations, which can be used to induce ultrasound. And so there are three main ingredients behind OBMD. So first of all, you need to make sure that you have particle exchange. This is simply done here via this relaxation type of equation, where delta n stands for the number of particles that needs to be inserted or deleted at a given time step. N0 is the current, N0 is the desired number of buffer particles, and n is the current number of particles. And here I mentioned this word buffer. So in this simulation boxes, you have a region of interest where you calculate all the properties that you want. And this is surrounded by a buffer region, which acts as a reservoir of particles and also linear momentum. And linear momentum is easily conserved with this second equation here. So you impose a certain flux, which you want, let's say, an oscillating pressure field or a shear flow. And this is done by adding forces to each of the buffer particles. And we also make sure that we measure, for example, if a particle goes out of the simulation box, that we measure the outgoing momentum, and also for the inserted particles. And how we do the insertion is you can have two different ways. So for simple molecules or point-like particles, you can directly insert the particles in the buffer region and use a kind of a steepest gradient descent method to find the optimal placement. But for more realistic or larger complex molecules, you facilitate the insertion by adaptive resolution technique, which is a multiscale technique, which relies on this transition between the coarse-grained force field and the atomistic force field. And with that in mind, of course, it's way easier to insert particles in a softer, in an environment with softer force fields. So that is why ADRES facilitates this insertion. And to go a little bit into the detail how we did implement this open molecular dynamics. So we combined three existing fixed styles in LAMMPS. So LAMMPS has these famous fixed styles, which are typically either integrators or some on-the-fly statistics. And we combine three of them, like fixed deposit, which is for particle insertion and measuring ingoing momentum, fixed evaporate for particle deletion and measuring the outgoing momentum, and fixed add force for adding the forces. And so we had in mind that we need to construct this as simple as possible so that the end user needs to modify their existing scripts as minimally as possible. So the only thing that you need to change is the boundary command, which you said, okay, you can use a 1D type of a spatial decomposition. And if you like to just open the system in one direction, you would specify this as F, and the other two directions you can give periodic boundary conditions, or you can alternatively open all three directions. And next you define the regions, for example, the buffers or the region of interest and so on. And in the end, the main part is you have to instantiate this fixed OBMD, which has many optional parameters to really control the last detail if you like. So for example, this additional shear stress that you impose on the boundaries, and also the type of the adding up the forces. There are different ways. We also have that, and also all the time scales, for example, for this insertion algorithm. And the next ingredient is this address. We have implemented this as an additional atom style. Why an additional atom style? Because all of these particles carry additional particle attributes. In this case, this is a weight factor, which tells you what kind of a resolution your particle has. So if it's in the coarse-grained region, it has one number, and if it goes to the atomistic region, it continuously it's a continuous function of the position of a particle. And we calculated these weight factors with defining additional fixed style, similarly as before. But the main part of this method lies in the pair styles. So this, for each of the pair styles, you need to actually implement two force fields. One is for the atomistic part, and the other is for the coarse-grained part. And so we did a strong scaling study of what happens, how the code is affected, how the speed of the code is affected when we add this additional OBMD stuff, and compare it if we just use pure LAMMPS. So we tested that on EuroHPC Vega supercomputer, using 250,000 of particles up to 33 million particles, and from 4 GPUs to 80 GPUs, which is a third of this GPU partition, if I'm not wrong. And we can see that the scaling is not affected by this addition of the OBMD code, except for a prefactor. But of course, because the OBMD code adds additional complexity. And there are, of course, room for improvement. We have already implemented the infrequent neighbor list builds. So you don't have to rebuild the neighbor lists if you're not inserting a particle or deleting a particle. And the next thing would be to change how neighbor lists are built, because you don't need to actually build it throughout the simulation box, but you only need these local changes because you're inserting the particles locally. And so as a showcase example, we have done a simple oscillation of the pressure at one end, at one of the buffers. So this would be a kind of a very simple representation of an ultrasound wave coming from one side. And so we see that on this center plot that the density profile is as expected. It's a sinusoidal profile with the correct frequency and wave vector, wave number. And it's also damped, which is expected since we have a viscous fluid. And on this right-hand side, we see that the attenuation factor increases as a square of the frequency, which is also in line with the theory. And this is also a very important parameter when you're doing actual ultrasound experiments. So you don't want the frequency to be too large, and then you wouldn't get any signal at all. And so as a future prospect, I mentioned coupling if you're really trying to describe the ultrasound on macroscopic scales, then you need to couple it to a solver for continuum hydrodynamics. And one ideal candidate for that is lattice-Boltzmann method. There we would use the waLBerla solver, and the communication between LAMMPS. So this is the part that would solve the motion of particles, and the communication to the waLBerla would be done through the flux exchange boundary conditions. So there would be a region where these two software packages would be communicating with each other. And yeah, that's kind of a future prospect. For now, this is a work in progress. And yeah, that's it from my side. If you have any questions, I would like to. Don't hesitate to ask.
It's gonna happen in Q&A session. Yeah. Thank you, Tilen, for this presentation. Let's continue with our agenda. So the next one on the list is actually Rodrigo Bartolomeo from Jülich Supercomputing Center, and he will explain us about the performance, portability, and scalability of codes, COCOS and all. Rodrigo, please.